The Theory of Nothing, How Everything Works and How It Was Created from Nothing, by Guy Abitbol. Before walking through the 25 proven steps of the theory, let's skip the whole document for the good order. This document is attached in the description. Step number 1 is the only not rigorously proved step in this theory, due to Gödel's incompleteness theorem. It states that nothing, or shape in space with existence contradiction, is always being created, with any relative velocity. For example, if we defined nothing as a zero-dimensional point, then a shape in which a point encloses a line, that encloses a sphere surface, that enclose a spherical volume, is a non-existing shape, because this shape will be always enclosed by nothing. And we can prove that any open shape can be enclosed by something. Similarly, a space that originates from a point can't be created, because we can prove that any space must have origin. And we defined point as nothing. The following steps are proven qualitatively and demonstrated through 8 files of 3-dimensional pictures, and 44 files of MATLAB simulations that are attached in the description. The certainty of the proofs is definite, because it is based on the pure derivation of classical mechanics as a mathematical theory. See Appendix. Step 2. When two high-velocity non-existing shapes collide, they deformed into two squashed non-existing shapes and move away from each other at lower speed. These squashed non-existing shapes will be referred to as g-particles. Step 3. If two g's collide, they bend at the collision point and rotate. Step 4. If two bent g's collide, they can be attached to each other and rotate together. Step 5. Further collisions, bendings and attachments create cluster. Step 6. As the cluster become larger and larger, any new attachment increases its size by only small amount. But if the new attachment changes the moment of inertia, such that the cluster now rotates about its intermediate moment of inertia, then the cluster changes its orientation dramatically during the motion. Even if the intermediate moment of inertia is just slightly bigger than the smallest moment of inertia. By the intermediate axis theorem. Now, because of the dramatic changes in orientation, further collisions can cause the cluster to reorient and to rotate about its largest moment of inertia, while preserving its angular momentum and losing rotational energy. By the major axis theorem. Thus, over time, any cluster acquires 2 equal moments of inertia, while rotating about its third larger moment of inertia. Step 7. The rotation of any body is governed only by solving the system of equations in the former page. Therefore, bodies with same moment of inertia rotate the same. And this cluster rotate exactly like Feynman's wobbling plate, even though it's asymmetric. And the cluster's angular velocity and major axis, both return to their positions each t sub L seconds. The functions that describe the cluster's angular velocity are simple harmonic oscillators and wave functions. Step 8. Because the cluster's major axis is the shortest, over time, more stuff collides in its direction than in the other directions, making the cluster thinner and thinner, until its large moment of inertia is about twice bigger than the other two. Step 9. Therefore, over time, any cluster acquires 2 equal moments of inertia, while mainly rotating about its third, twice bigger moment of inertia. And the time taken for the major axis to return to its positions is 1/2 of the time taken to the other 2 axes to return to their former positions. Step 10. When the formed cluster collide with g's, it bent them at the collision point, rotate them and throw them with high speed, creating g sub z, which we call electric field, or g sub xy, which we call magnetic field. Step 11. Over time all the clusters in the universe throw g sub z and g sub xy on each other. That cause them to attach or detach subparticles, and to adjust orientation. The equilibrium of these collisions creates types of clusters differing in the number of their subparticles, or mass. Step 12. Because the clusters throw many g's on each other, some g's increase the magnitude of the cluster's angular momentum, and some decrease it. Such that, at equilibrium, this magnitude is equal for all clusters. By the theory of synchronization. And because the major axis period, t sub L, is inversely proportional to this magnitude, and proportional to the major moment of inertia, the major axes of all same-type clusters align with the world z-axis, simultaneously. However, different particles of the same type have different direction of angular momentum, which is restricted to one of two spherical zones, which we call positive and negative charge. There is a transformation that transform between any spatial direction to a direction in the spherical zone. This corresponding spatial direction, from now on referred to as L sub q, is what quantum mechanics mistakenly taken as the particle angular momentum. What we call magnetic field direction is equal to L sub q for a positive charge, and opposite for negative charge. Step 13. We can see that positron create G sub Z plus, and electron create G sub Z minus. What we call electric field direction at a point, is the flying direction of G sub Z plus there. Or the opposite flying direction of G sub Z minus there. The collision of G sub Z is more powerful when its tangential velocity is in the same direction as its translational velocity. And the collision response is dictated by the collision point. Therefore, because the electron and positron clusters contain many bended edges, we can see that when G sub Z minus collide with electron it repels it from its source. And when it collides with positron it attracts it. Therefore, like charges repel and opposite charges attract, with a force inversely proportional to the distance squared, because G sub Z are geometrically diluted in three-dimensional space. Step 14. The period of the electron's major axis is half of the period of its other axes. Thus two different facets are capable of throwing G sub x plus in the direction of the electron's magnetic field, but only one facet is capable of throwing G sub x plus in a specific perpendicular direction. Therefore, the electron's magnetic field is twice stronger in the direction of its primary magnetic field, than in any perpendicular direction. The plane perpendicular to the angular momentum represents the average cluster orientation. Electron and positron with same magnetic field have exactly opposite angular momentum, and thus the same average cluster orientation. Therefore, they behave the same in magnetic field. Taking into account the tangential velocity of the average cluster orientation, and the geometric dilution and rotation of G sub xy, we can see that two electrons with same magnetic field attract if positioned along their magnetic field and repel if positioned perpendicularly. Similarly, taking into account also the G sub xy flying direction and its collision point, we can prove any force and torque exerted by a magnetic field. While the information about the electron's angular momentum is sufficient to dictate most of its electric and magnetic interactions, as described by the Maxwell equations, a more precise description requires also information about the angular velocity and whether it's in an odd or even round. As real electron period involve two rounds of angular velocity about the angular momentum. This odd or even round will be referred to as phase. This more precise description is captured in the quantum spin state, because it is derived from a wave function, and any wave function satisfy the simple harmonic oscillator equation, which describe our cluster's angular velocity direction and phase. For a moving electron, a more precise description requires also information about its velocity and its distance to the target. In order to determine in what direction of angular velocity and phase the electron will arrive, This information is also incorporated to the wave function in quantum mechanics by the dot product of the particle's momentum and the target position vector. We can see from the interaction pictures that electron in external homogeneous magnetic field feels torque but not force, and that electron and positron with same magnetic field feel same torque, but precess in opposite direction about the external magnetic field, because they have opposite angular momentum. This is a torque-induced precession, which we call Larmor precession. In contrast to the torque-free precession of the electron, that described previously and create the T sub L period. The duration of one round of Larmor precession equal to the product of T sub L with an odd integer. Thus, after one round, the angular velocity of the electron returns to its starting point. But its non-major axes complete only half round. Therefore, the electron returns to its starting orientation only after 2 rounds of Larmor precession. Step 15. Charge that move in external magnetic field feel force perpendicular to their movement and to the external magnetic field in a charge-dependent direction. This is what we call Lorentz force, and it is demonstrated by examining the most powerful collision of G sub xy into a plane representing the average cluster orientation and rotation of the charge. Step 16. Moving charge generates internal magnetic field, perpendicularly to its movement and to the examined point, in a charge-dependent direction. This is what we call O Savart Law, and it is demonstrated by examining the collision of the plane representing the average cluster orientation and rotation of the charge, into a G particle due to the charge movement, and the resulting bended particle, that thrown into the examined point. Step 17. In Stern-Gerlach experiment we fire electrons through inhomogeneous magnetic field. Because of the movement of the electrons, G sub xy from the magnetic field hit them in various points, and exert a changing torque on them, which align their internal magnetic field, parallel or anti-parallel, to the external inhomogeneous magnetic field. As previously demonstrated, after this alignment, torque is no longer being exerted on the electrons, and an equal force push them upward or downward, depending on their internal magnetic field orientation, creating 2 distinct parts on the screen. The probability that the electron's internal magnetic field will be aligned parallel to the external magnetic field depends on G sub xy collision point, which depends on what amount the internal and the external magnetic fields go in the same direction, in other words, in their dot product, or in the cosine of the angle between them. However, the cosine range is 1 and -1, and a probability range is 1 and 0. A simple range conversion and some trigonometric identities show that this probability equal to the square cosine of half the angle. Exactly what we get from quantum mechanics. Step 18. The electron and positron angular momentum is restricted to a spherical zone, such that, when it aligns parallel or anti-parallel to its major axis, it can take infinite values. But otherwise it is restricted to one value. During Larmor precession, the internal magnetic field and L sub q is really precess about the external magnetic field. We can use the previously mentioned transformation to transform between the internal magnetic field to the angular momentum during a Stern-Gerlach separation. An indelicate Larmor precession can also contribute to the equal separation pattern observed when applying consecutive perpendicular Stern-Gerlach apparatus. Step 19. G particle is created by a powerful collision of 2 non-existing spheres, and thus, having a maximally thin oblate spheroid shape. When G particle collides with positron, it bends, such that it has plan of symmetry, where the normal of this plan is its angular velocity. Thus, its angular velocity aligns with its angular momentum. The impulse of collision between positron and G particle is referred to as non-bending impulse, if it's the biggest collision impulse that doesn't cause G bending. In our universe, the non-bending impulse is constant, such that the speed of its emitted G is the speed of light. Any bigger collision impulse will cause G bending, and is referred to as a bending impulse. However, only the impulse at the last contact point dictates the speed of the emitted G particle. Therefore, any bigger collision impulse will continue to bend G at their contact point. And this point won't be the last contact point until the collision impulse reaches the magnitude of the non-bending impulse. Thus, any collision impulse will emit any bended G at the speed of light. In other words, the speed of the electric and magnetic field particle is always the speed of light, regardless of the velocity of their source. While stationary and uniformly moving charge collide with G only once, an accelerating charge collide with G twice, and thus bends it twice. This twice-bended G is what we call photon. The stronger the collisions, the larger the magnitude of the photon angular velocity and its deformation. But larger deformation has smaller moment of inertia. Thus, the magnitude of the photon angular momentum, which is the product of its moment of inertia with its angular velocity, remains constant for any photon, and equal to the reduced Planck constant. On the contrary, the photon rotational energy, which is half the dot product of its angular momentum with its angular velocity, increases as the magnitude of the photon angular velocity increases. As demonstrated in page 16 and 33, even though each photon has a non-symmetric shape, its angular velocity still undergoes some kind of indelicate precession about its angular momentum. Let's define T sub f as the time taken for the photon angular velocity to approximately return to its initial position. Therefore, the photon frequency is 1 over T sub f. Because the magnitude of the photon angular momentum is constant and equal to the reduced Planck constant, if we use change of variables in the integral that calculate the photon rotational energy, we can show that the photon rotational energy is equal to the product of its frequency and Planck constant. Therefore, the total energy of any photon is greater from the known hf by a constant. But in any experiment this constant is reduced. See page 23. If a stationary charge begins an accelerated motion, it generates photon, the magnetic component of the photon must have a direction perpendicular to the acceleration and to the photon location, in a charge-dependent direction. This is a consequence of the Leonard-Wiechert equation, which stem directly from Maxwell's equations. This is demonstrated in the following pictures, that examine the collision of the charge with G particle, due to its acceleration, and the resulting photon in its examination point. The electric component of the photon is generated by the second collision, and thus it's perpendicular to its magnetic component, and to its velocity. In the former page I have demonstrated how a bigger collision impulse, between a charge and G particle, increases the amount of G bending, and its angular velocity, while decreasing its moment of inertia, such that the magnitude of its angular momentum remains constant. And I have also shown that any photon frequency can be obtained by this mechanism. Furthermore, I have also demonstrated that a bended G with larger angular velocity will cause more powerful subsequent collision with another electron, rather than a bended G with smaller angular velocity, even though its moment of inertia is smaller, and even though they both have the same magnitude of angular momentum. This explains why only high-frequency photons are capable of ejecting electron in the photoelectric effect. Moreover, the former page also explains why the speed of any photon is the speed of light, regardless the velocity of its source or its frequency. Because the shape of the bended G doesn't matter. What does matter is the impulse exerted on its last contact point. impulse bigger than the non-bending impulse will continue to bend g, until it reaches the value of the non-bending impulse, which cause emission at the speed of light. Step 20. What we call left and right circularly polarized photons are photons that their angular momentum is parallel and anti-parallel to their velocity, respectively. Therefore, their precessing angular velocity create rotational effect when hit a target. What we call linearly polarized photon is photon that its angular momentum is perpendicular to its velocity. We mistakenly say that it has no angular momentum. The other photons are elliptically polarized photons. What we call polarizer is long sheets of molecules that are capable of moving only parallel or anti-parallel to a specific direction, referred to as the polarizer direction. The more the photon angular momentum is perpendicular to the polarizer direction, the more probable that it will pass through it. Because this photon will be capable of moving the polarizer upon collision. And the polarizer's moving particles will in turn collide with another G and generate another photon with the same properties and direction. This is because the photon tangential velocity is much greater than its translational velocity. What we call photon polarization direction is a unit direction perpendicular to its velocity and to its angular momentum. Therefore, we can calculate the Malice's law, which is the probability that a photon will pass through a polarizer, by calculating in what amount the photon angular momentum is perpendicular to the polarizer direction, which is their absolute cross product. Thus, using some mathematical identities, we arrive at the Malice photon passing probability, which is the square cosine of the angle between the polarizer direction and the photon polarization direction. Similarly, using also the Lienard-Wiechert equation, we can prove the properties of polarization by scattering. Antenna that creates vertical photon polarization direction, orient vertically, such that the moving electron will hit G particle and rotate it with angular momentum perpendicular to its emitted velocity and to its polarization direction. Using potential energy consideration, we can show that the wavelength of the created photon is twice the length of the antenna. Similarly, antenna that create horizontal photon polarization, orient horizontally. An helical antenna can be used to create circular polarized photon. Step 21. The Robbie cycle. The internal magnetic field of an electron will precess an external homogeneous magnetic field, such that it returns to its initial position each odd integer multiples of T sub L, referred to as T sub W. Therefore, the electron's angular velocity also returns to its position each T sub W seconds. And as expected, T sub W is proportional to the electron mass, and inversely proportional to the electron charge, and to the magnetic field magnitude. If we rotate a second external homogeneous magnetic field, perpendicularly to the first, such that its direction returns to its initial direction each T sub W seconds, then its emitted G sub xy will always hit the electron face in an opposite direction of its motion, creating a strong force that flip the electron internal magnetic field, or its L sub q. As expected, the time taken for this flip is proportional to the electron mass, and inversely proportional to the electron charge, and to the rotating magnetic field magnitude. As expected, in order to flip the electron, instead of using the rotating magnetic field, we can also fire circularly polarized photons with T sub f, that equal to T sub W, at a direction perpendicular to the first external magnetic field. Step 22. Quantum electrodynamics. Because the photon tangential velocity is much greater than its translational velocity, and because its angular velocity approximately rotates about its angular momentum, there will be a point on the photon that always hit the target first. The normal at this point dictate the photon exerted force direction on the target. The total effect of many colliding photons can be roughly calculated by summing up all these exerted forces directions. Because each photon travel at the speed of light, we can calculate its travel time duration, dt, and then its exerted force direction, by rotating the initial exerted force about the photon angular momentum by the product of dt and 2 pi over t sub f radians. We can use this technique to prove the law of reflection, but also to prove diffraction grating, and any other law involving photons. While the rotating photon approximately returned to its orientation each t sub f seconds, the rotating magnetic and electric field particles exactly return to their orientation, because their angular velocity and angular momentum are parallel. And that is the reason that we were able to predict the electron magnetic moment to a very high accuracy. Step 24. Gravity. In the universe, everywhere and every time non-existing shapes can be created, with any relative velocity. Therefore, any object will feel collision forces from all directions, which on average cancel each other out. But if two objects stand close to each other, they will feel less collision forces from the side that in between them, because each act like a barrier that prevent collisions from far created non-existent shapes. Thus, the amount of these prevented forces of collisions that goes in the direction of these two objects is equal to the exerted gravitational force from the other side that each object feels. Therefore, we can calculate the gravitational force by summing up all these prevented forces that goes in the direction of these two objects, using a double integral over the blocked spherical area. We can see that this calculated force, like the Newton gravitational force, is inversely proportional to the squared distance of these objects. Additionally, this calculated force is proportional to the products of the two objects' surface area, which is an expression to their mass. This explains why anybody falls with the same acceleration, regardless of its mass, as it just cancels out, because acceleration is force over the accelerated mass. Gravitational redshift is caused by the movement of the electron that create the photon or by the movement of the electron in the receiver. In both cases, the change in the collision impulse of this electron, with G particle or with photon, is increased with gravity. Similarly, massive object bends light, because the light is reflected from electron that is accelerated due to gravity. And gravitational time dilation is caused by electrons' distance elongation due to gravitational forces. Step 25. Entanglement. If charge collide with G particle, it bends, rotates and emits it at the speed of light, always, because the deformation reduces the collision energy. However, in the universe, there are also small spherical-shaped clusters that are not capable of being deformed, referred to as O particles. Therefore, if electron collide with O particle, it emits it with a speed much greater than the speed of light, because there is no energy loss to deformation. See Step 29. This O particle can be thrown back and forth between two electrons with opposite internal magnetic field, creating what we call entangled particles. Thus, if we change the internal magnetic field of one electron, the O particle will hit the other electron in a different point and change its internal magnetic field to be again opposite of the first. Entangled photons are created when the electron in their transmitter is entangled to the electron of their receiver, or polarizer. See Appendix.